Okay, chapter 6, problems. Then I'll be sending out a quiz later today. So the first one here is 3.2, and we have water, a plastic layer, and steel. And it's amazing, but you can arrange this such that there's perfect, complete transmission. That's the problem here. So we're going to adjust the thickness of the plastic. And also we don't know the, we have to determine what the speed of sound is needed in the plastic. So there are constraints here, but it is possible to get complete transmission. Now, in this case, when the incident medium is the same as is not the same as the transmission medium, you need to think there's two ways you can go here on the complete transmission for normal incidence. When the two mediums are the same, you can get it if you choose the thickness to be a half integral number of wavelengths. Because then it's like it's not there at all. And if the medium is the same, you're going to get complete transmission. In this case, that's not going to help you because you got water here and steel here. So you got to find, there's another way. And the other way is the so-called quarter wave, it's known as the quarter wavelength, as a quarter wavelength plate. Okay, we showed in lecture that if the specific acoustic impedance here is the geometric mean of these two, and this is the wavelength in here is if the width here is 1/4 of a wavelength, or 3/4, or 5/4, etc. Okay. Now we're going to go for the smallest distance here because I think they ask for no, I'm mixing this up with the quiz. We're going to go with the lowest frequency. So, all right, which is going to give us, this is the longest wavelength. So it's where the length is 1/4 of a wavelength rather than 3/4 of a wavelength. So we need two conditions here, the geometric mean condition and then the length condition here. The geometric mean, because we know the specific acoustic impedance. You can look that up in the back of the book. For the water and the steel, we get these values. We can find the specific acoustic impedance of the plastic. Okay, now I'm lost here. Are we given the density? Yeah, there it is. Okay. So we're given the density of the plastic. So therefore we know the speed of sound. We can calculate it. It's just going to be the specific acoustic impedance divided by the density. So we get a number. It's 5560 meters per second. And as I said before, the length here, we'll set it equal to 1/4 wavelength, or this quarter wavelength plate, which makes it easy to remember. And that's easy because we know the frequency, we know the speed of sound, so we get about 7 centimeters. And oh, by the way, if it's oblique incidence, forget it. Okay, this is just for normal incidence. We only derive this for normal incidence, right? Okay, any questions on that one? The next one is 3.3. So now we have the same medium on either side of a slab or a layer here. This is 3.3. We have 2 kilohertz. It's normal incidence. We know the thickness. There it is, 1.5 centimeters. We know the material. So this is straightforward. What is the transmission loss here expressed in dB? Okay. And what is the power reflection coefficient? Okay, and I think you'll notice this stuff continually evolves, and so I've had to cut out, in order to fit everything in, I've had to cut out and restrict it. That's the main reason. There's restrictions to just certain parts. Sometimes the parts just aren't good. I think in one case here, I got tired of fighting. It just wasn't a good problem, so I deleted it. So that's why you'll notice see some of these omitted parts here. Okay, so the intensity transmission coefficient. There's a formula for that we discussed. Here it is. Now this is exact. It's a special case of a more general formula where you have different mediums on here. But when you set those mediums equal to be the same, this is what you get, and there are no approximations here. Right? However, what do we have here? We've got water and steel. Oh, and we dealt with water and steel before as an example in lecture, didn't we? The sonar dome. So if you look up the specific acoustic impedances here, they deviate significantly, I don't know if you could say substantially. But the point here is that what we're interested in is the ratio R2 over R1 compared to R1 over R2. So even though the ratio is not huge or is not huge here, when you look at this difference, this is going to be much bigger than that, as we discussed in class. So it's a good approximation here to kill that. So I've stated it right here. So we make that approximation. We need to find K2L. And sometimes, this could be a thin layer. If it's a thin layer, that means you have the nice simplification. You don't have to worry about the sign here. But let's see if it's a thin layer. So this dimensionless quantity K2L is the wave number, which is the frequency divided by the speed of sound times the length. This is the angular frequency, so it's 2 pi times the actual frequency in hertz divided by the speed. Plug the numbers in, and it's small. So we have a thin layer, what's called a thin layer here. That's what we mean by thin. When the wavelength is large compared to the thickness. So that means we don't have to worry about the sign here, but you do have to square this, of course. So we get to this formula. And now we have this interesting cases I mentioned in the lecture where we have a small number here and a big number here. And you can get anything when you multiply a small and a big number together. And in our case, it's fairly small. I can see from the result here. I can see that this is fairly small, but it's not, not especially small. But anyway, you punch it in and you get about 80% for the transmission. 80% of the incident intensity is transmitted through here, comes out. And acousticians often will express this as a dB loss. Okay, so what's the dB loss? It's the change in dB. So as we discussed, and you can imagine writing this out here, it's 10 times the log of the intensity divided by the reference, the intensity that gets through, minus 10 times the log of the incident intensity divided by the reference. You can combine those into just the ratio of the intensity, right? This is commonly done. The reference drops out. And the ratio of the intensities here is by definition, okay. In this case, because it's the same medium, the intensity transmission coefficient is identical to just the ratio of the intensities. You don't have to worry about those impedance complications here. It's the same medium. So you punch this in and you get it's about a dB down. Part B of 3.3, what is the power reflection coefficient? Oh, well, that's easy. We found the power transmission coefficient. Energy conservation tells us that the fraction of the intensity that's reflected plus the fraction that's transmitted has to be 1, because we have no sinks of energy. We're not losing energy anywhere here. There's no losses in the slab. We're neglecting those. And that's often a good approximation, incidentally. So we have to have the sum of these two equal 1. So we get, if 80% roughly of the intensity is transmitted, 20% is going to be reflected. And I want to remind you here, you got to be careful with this. What's conserved here is the power, the energy per unit time. So we can get away with this because it's normal incidence. We don't have to worry about that area problem. So if it's oblique incidence, you won't have this. So you need to be careful about that. Then you have to put a capital pi here. It's the power, and there's a difference between the coefficients here in that case. Okay, any questions about this one? Pretty straightforward. They get more interesting here in this problem set, more challenging. So 4.2 is an inverse problem. We don't know what this medium is. Well, we don't know specifically. We don't know the density, and we don't know the speed of sound, which means we also don't know the specific acoustic impedance. So this is 4.2. Okay, so here's the data that we have. You think of this as like experimental data. Is that at normal incidence, half the amplitude's down by a factor of, the reflected amplitude is 1/2 the incident amplitude. That means the reflection coefficient is 1/2. However, we don't have phase information. All we have is the magnitude, the amplitudes. We know that the reflected amplitude is down by a factor of half. We don't know its phase. So the reflection coefficient, which contains phase information, can be plus or minus 1/2. Right? All we know is the magnitude. As the angle of incidence is increased from 0, the magnetic reflection coefficient goes down, and it goes to 0 at some angle. We don't know that angle, but we know it goes to 0. So immediately, what you want to think here is this is intromission. This angle right here, if we knew it, would be the angle of intromission. So we have that phenomenon occurring here because there's no reflection, right? And it's certainly not. For oblique incidence, this is the only way you get perfect transmission, right? You have to be at the angle of intromission. For our case here, of a single interface, there's no slab here. Okay, and then we find at 30 degrees what's happening. Now everything is reflected at 30 degrees, and you know what that is. That's going to be total internal reflection is occurring here in this region. And this would be the so-called critical angle. So to get at this, and we want to find this with this, the medium here. We want to identify this medium. So we'll find the speed of sound and the density. The first thing that I would do here, I'd go for the simplest thing, and that's the critical angle. We know from Snell's law. Remember, Snell's law is just this. I'm going to write it in terms of the sine of 1 and 2, but you can put in the sine. You can make this I and T if you want. It's just easier. So this is Snell's law. And at the critical angle, this is 90 degrees. So this becomes just 1. So that allows us to find, in this case, this becomes the critical angle. That allows us to easily find the critical angle. Its sine has to be theta, sine C1 over C2. So we can find C2. That's good. That's one of the things we wanted to find. So it's just go for the simplest thing first. It's 3,000 meters per second. Okay. Now, I told you in lecture that we have these formulas for the angle of intromission. It only works in 2 of the 4 possible cases. And I told you you don't have to remember those cases. Well, what I should have said was usually you don't have to worry about that. You can just use the formula, and it'll tell you whether the angle of intromission exists or not. Right? That's reasonable. Well, this is an exception. It's unusual, but this is an exception. Here you have to actually go look it up or figure it out. These are the 2 cases. Okay, and the reason we have to do this is basically because this is an inverse problem. We don't know what this medium is. Here are the 2 possible cases for which the formula yields an angle of intromission, 2 of the 4. Now, our case, we have this right here. We have C2 greater than C1. So therefore, because we have an angle of intromission, we have to have R1 greater than R2. The specific acoustic impedance here has to be greater than there. Why is that important? Well, If R1 is greater than R2, what's the sign of our reflection coefficient have to be? It's got to be negative. Now, we didn't know that, and that wasn't measured, but we've been able to figure it out, right? We've been able to figure it out by the fact that an angle of intromission exists here. So that's information, and we've now used it. So now we know what the reflection coefficient is. It's not plus 1/2, it's got to be minus 1/2. And that's important. As we saw, we've seen examples of this before, either in lecture or in problem set. You know, that sign makes a big difference. So once you know that, you can find R2. This is easy algebra here. Once you know that this is minus 1/2, it's easy to find the ratio. So I was running out of space here, it looks like, so I got a little briefer. But you can easily solve for R2 now that we know precisely what the reflection coefficient is. And we get 5 times 10 to the 5th in SI units. Once we know the specific acoustic impedance and we know the speed of sound, we can get the density, and it's this. Okay, a little more interesting. That's a little bit more interesting, right? Any questions about that one? Some of these are good problems. Oh, this is a straightforward problem, but again, we'll get more interesting. So this is 4.4. We've got water and mud here, and the mud is acting like a fluid, and you might think, oh, mud can be hard, can't it? So they're not thinking of that here. We're thinking that, you know, it's in contact with the water, so some water is down in here. Now, just as a little digression here, there could be a shear wave in this mud, okay? And that's non-acoustics. If we've got shear waves, our theory is going to fall apart. We're just dealing with compressional waves here. However, if you get a shear wave in this mud here, and it's not dry mud, this is wet, this is going to be wet mud, right? Because of the water up there. You can generate a shear wave. How far do you think it'll go? What's your wild guess? It's probably not going to last very long. It's probably going to be severely attenuated. So even if there are I'm just pointing this out, even if there are shear waves in this mud here, if they're highly attenuated, our theory is probably a good approximation, I would think. But that's a little, it's not so obvious, actually, now that I think about it. You know, you'd want to be careful about that if you make that approximation. It's not an approximation, it's an assumption, okay? Because it's not like anything quantitative here. Our theory it's for fluids. Our theory is just for fluids. Shear waves are generated here. It could mess up, these results may not be accurate. But I have a feeling that even if there are shear waves and they don't last, they attenuate very severely, then it would seem reasonable that the theory would be a good approximation. So we're given the incident pressure amplitude here and the angle of incidence. It's 45 degrees. We know the mediums. We're given all the information on the mediums. That means we can find the specific wave impedances. Here they are, the product. Okay, they differ by a factor of 2. And the first part here is compute it's straightforward, right? The angle of transmission. We get it from Snell's law. Here it is, slightly different notation, but this is Snell's law. We can find the transmission angle, and it's 28 degrees. Okay. Part B is the transmitted pressure amplitude. So when we have an angle of incidence here, this is more complicated, right? And as I mentioned in lecture, people usually do it with the Rayleigh reflection coefficient, okay? And here it is. But we're asked for the transmission coefficient. However, we know that the pressure has to be continuous. The incident pressure here on the total pressure on the incident side has to be instantaneously the same pressure just below there. You have to have continuity of pressure. And as we showed in class, that leads to this relationship between the reflection coefficient and the transmission coefficient. We showed that. It's not just true normally, it's true obliquely here too. You can go back and look at that. That was, we got to this by establishing Snell's law and the fact that the angle of incidence equals the angle of reflection. Once you got those two things, the oblique case, just for continuity of pressure, just degenerates down to this very simple relationship that we first found for the normal incidence. Now it turns out you actually you want to calculate this number for later on, and I didn't realize that. So it's good to actually calculate. Here it is, calculate this number. It's 0.033. So I add 1 to it, sort of 3 figures, I get a transmission coefficient of 1.03. And here it is. I had forgotten. So we have a transmitted wave. The transmission coefficient is greater than unity. Did we make a mistake? Are we violating energy conservation? Remember this? This seems like a long time ago. It wasn't that long ago. But I warned you that it's the energy that's conserved here. Okay? Transmission and reflection coefficients, those are amplitudes. And it is possible to actually have a transmission coefficient, which is the ratio of the amplitude of the transmitted wave to the incident wave. It can be greater than unity. It doesn't violate energy conservation. It depends on it's because we have a different medium here. There's no violation of energy conservation. Yeah, I think I promised you that we would see this somewhere, and then I forgot about it, but I guess here it is. And I don't think we've seen it in another case. Does anybody remember in a problem? It just doesn't look like you care. But I think it's interesting, because I remember one time teaching this course, I looked at this and I go, oh no, it's got to be wrong. We're not conserving energy. We are. You can verify that energy is conserved here. This is for amplitudes here, not energy. And it depends on the medium, different medium. Okay, so once we know the transmission coefficient, we can get the transmitted pressure, and here it is. It's greater than this, okay, because this is greater than 1, but that's no problem, as I said. And here, they also ask for the reflected pressure amplitude, and that we get from the reflection coefficient. So that's why you want to determine this. Okay. And you might think, well, I can just get it from T, but then we have a round-off problem here. See, I rounded this off. Right, so that's why I went ahead and calculated this. So the reflected pressure amplitude is going to be 3.3 Pascal, and the power reflection coefficient is simply, you can look this up if you don't remember, is simply the square modulus of the reflection coefficient. And it's about 1,000th. It's small. And we've got right. So the power here, there's almost all the power is being transmitted, right? And part of that, you want to be a little careful because we got an angle of incidence here. This is not normal, but the specific acoustic impedances are not too far apart, right? They're, this is 1.5, this is 2, so we're in the region of a matched impedance. So that's why this is so low. But the reason I said you want to be careful is, what happens if I increase this angle of incidence here so that we start to get towards grazing? What do you think? We established this, but it's all math. But what do you think happens to a wave when it grazes? What do you think is going to tend to happen to the wave, the energy? The energy is going to tend to be reflected. So this will go up. If you increase that angle there, it'll go up a lot. So it's not just matched impedance here. Now, if you exactly match the impedances, it's over. You're going to have, it's the same medium. So even at grazing, you'll get complete transmission if they're exactly the same. Yes?
Can we have the same assumption from the amplitude of transmission and reflection? because one of them is, when you look at the absolute of reflect, it's very small when you compare it to the transmission. So can we make an assumption that most of the energy is transmitted?
Yeah, it's approximately all of the energy is transmitted here.
Can we see it from the amplitude, because transmission amplitude is higher than, much higher than the reflected one? Can we relate it with the energy?
Oh yeah, we can calculate. Well, I mean, this is the calculation. This is the power reflection coefficient. So this is the fraction of the incident power that is reflected. It's about 1,000. You know, it's 1/10%, roughly. So of the power that's coming in here, 1/10% is being reflected, and the remainder is going through. Does that answer your? Yeah, it's right there. That's what that quantity is.
From the amplitude-wise, when you think just the amplitude of the transmission reflection coefficient, so can we say most of the energy is reflected because, sorry, transmitted because the amplitude of transmission is higher than the reflected one? One of them is 103 and 1.2.
Oh yeah, I see what you're getting at. I think it's dangerous. Yeah, like I was saying earlier, the amplitude of the transmitted wave is greater than the amplitude of the incident wave, which is remarkable. It doesn't seem right. But I think it's dangerous to conclude that nearly all of the energy is being transmitted without calculating, because I would hesitate to make a statement about that. Because you might find a weird situation where this could be significantly greater here, could be significantly greater, but just depending upon the parameters here, it depends on the parameters. I'm sure in fact, I would bet you can find a situation where, a significant fraction of the energy will be reflected here, even though this amplitude is, higher. Yeah. Okay. Now, so this one's typed, right? Oh, it's right. We've got. So it's kind of small. Well, it looks small to me. It probably doesn't look small to you. But let's just do it this way. Now, why is this typed? There was a while when I did this in lecture, but it just was too much. It was too much to get the Chapter 6 material, to finish it, lecturing on it in 4 lectures. It was too much, and it's a little too involved. So I made it into a problem. It was after I typed the lecture notes. So that's why this is typed. Okay, is that clear? If it's not, it doesn't matter. Just don't worry about it. Okay. So here's a 4.6. And this is a challenging problem, okay? And it's a kind of inverse problem. We don't know the angular incidence here, okay? We know the power reflection coefficient. So we don't have phase information, okay? We do know the mediums, okay? So it's not an inverse problem in regard to the mediums. We do know the mediums. Those are nailed down here. And I got to tell you right now, if you sort of step back and look at this problem, I don't think it's obvious that you can determine the angular incidence. We don't have phase information, right? So I don't know if it's obvious. It turns out you can, but it takes some effort. So let's go through this. Now KFC asked for the. Sorry. Let me preface this. You'll notice that. Why did I draw this bending outward? The refraction here is this way. Why did I do that? Well, you look at the speeds of sound, right? And the speed of sound is greater in this material. So you can think it's analogous to like glass and air for light. And there you get total internal reflection. As I told you, that's why it's called internal, to think of vacuum and glass here. So because the, however you want to look at it, but because the speed of sound is greater, you can see from Snell's law that it's going to have to bend outward. That means that at some angle here, there's going to be total internal reflection beyond that angle. So it's good to, even though it's not directly related into the problem, KFCS asks you to calculate it. It's a good idea to calculate, and you'll see why when we get to the end of the problem. It's easy to calculate. So here it is. Here's Snell's law. From that, we find the critical angle, as we've seen, is given by this. So it's about 70 degrees. Okay, so it's about 70 degrees. Now, well, I'll tell you right now why it's good to calculate this. Are we getting total transmission here? Is there total internal reflection here? No, because this is not 1. So in the end, when we find this theta, it had better be less than 70, 69 point, whatever it is. It had better be less than the critical angle. Because if it were equal to or greater than the critical angle, we would have, that R would be 1. So that's a check on our solutions. That's why it's good to calculate this. And like I said, it's an easy thing to do. Okay, so how do we solve this problem? Well, what you do is you just start writing things down. Because, it's hard to see through this, right? So you just kind of write, see what you know here. And what we know is the Rayleigh reflection coefficient. All right, there it is. It's exact. It's no approximations here. All right. Now, because we have this power reflection coefficient less than 1, we don't have total internal reflection. So we have to have this will be real. Now, you remember, the way we unify this with total internal reflection is the angle actually becomes imaginary, or the cosine of theta t becomes imaginary. Remember that? So that we mathematically unify the total internal reflection with this. So that's why I made this kind of strange sounding statement here. The cosine of theta t is real. That seems kind of strange to me now, but it makes sense in terms of that unification. But anyway, it's clear here, because we're not in the total internal reflection regime, this is going to be real. It's going to have to be real. Okay? That's all I'm trying to establish here, is that this is real. Remember, when you're beyond the critical angle, it's e to the I phi. It's a complex number. Looks kind of big. Okay. So we know the power reflection coefficient is 1/4. The power reflection coefficient is simply r squared, the modulus, but r is real, so I'm dropping the modulus signs. Okay, it's a real quantity. So here we are. We've been through this before, right? The reflection coefficient is plus or minus 1/2. In fact, I guess it's the same value that we can count. We don't know what it is exactly, but we've narrowed it down to two possibilities. So how do we proceed here? Well, here's the way I didn't know what to do. So I see this kind of complicated expression here. We're after theta I. We don't know theta I, therefore we don't know theta t. I'm going to call this something, alpha. I call it alpha. So the Rayleigh reflection coefficient has this form, okay, where alpha is the ratio of the cosines. This r here is, of course, I've gone to dimensionless wave impedances. I've taken, r is R2 over R1. That's all that's relevant right now, right here, right now. So I'm going to go ahead, I can calculate that, so I'm going to go ahead and calculate it. Now alpha, by definition, is this. By Snell's law, I know that alpha has to be the transmission angle. I can get rid of it in terms of the incident angle using Snell's law. So I get this expression for alpha. Okay? So the idea here is this. If we can find alpha, we can find the angle of incidence. Okay? So this is, if you might find another way of doing this. Okay? This is not unusual for difficult inverse problems. Just different people find different ways. Okay? So this is the way I did it. So I can see here that once I know alpha, and alpha is appearing simply here, I can find theta I. In fact, I'm going to go ahead and invert it. I can solve for theta I here, and you can check the algebra. And again, if there's a mistake, let me know. I think it's right. Here's the angle of incidence. This is what we're after. Once I find alpha, I can find the angle of incidence. So how do I find alpha? Well, from the data given. Well, what do I know here? I know that we have to have theta t greater than theta I. That means, if you think about it a little bit, that means the cosine, you can see this in your head, the cosine of theta t has to be less than the cosine of theta I. Okay? So what that means is alpha has to be less than 1. Alpha's got to be less than 1. Okay? So what are the r's? Oh, that ratio is greater than 1. So what do we conclude? R has to be what? Positive or negative? It's got to be positive. Right? So I know this is strange. And it requires some creativity, but I think it's good. And it kind of exercises your brain, you know. So you can find another way. And if your way is significantly better than mine, come and see me. And I'll rewrite this, okay? So anyway, through this alpha business here that I introduced, we conclude from our data that R has to be positive. So it's got to be 1/2. It's over. At this point, we're done. It's easy at this point. Because once I know precisely the reflection coefficient with the phase, I can find alpha. From alpha, I can plug it into this formula right up there, and I can find the angle. And look at the value. That checks what, right? Because it's less. It's less than 69.6. So that's a check on the solution. Yeah, interesting problem. Okay, any question about that one? So the next one is a classic full screen mode. You remember to learn the method of images, we use this. This is the way it's normally done. You go through an example, and the simplest example, I think the simplest in acoustics, is this rigid plane with a spherically symmetric source here. And then we argued that the sound field here has to be the same if you remove the plane and put a so-called image source here, identical to that, but on opposite distance on the other side. In this problem, we don't have a rigid boundary. We have a pressure release boundary. So this could be like water and air, for example. So in that case, what do you do to meet you don't want to have any acoustic pressure swing here. So if you look at a point on the surface here, they're going to be, we clearly want our image to be here, right? The same distance. So these distances are the same. So the pressure amplitude from here will be identical to the pressure amplitude there. But to get it to be 0, what do I need to do? I need to introduce a 180-degree phase difference here. So I'm going to denote that by an open circle. And that's going to be useful that notation is going to be useful for the next problem. So clearly, that's going to give us, if any point on the surface is going to be equidistant from these two sources, and if they're identical sources, same amplitude, same frequency, but they're 180 degrees out of phase, you're going to get 0 sound field here, instantaneous, no acoustic pressure. So that's the first thing to notice here. Now we're going to make our standard approximation of the far field. We're going to assume that R is much greater than D. So here's our, now, the surface is gone. The surface is gone now. We have this one medium that's everywhere, and we have these two equal and opposite sources. We have this image source is equal and opposite. That gives us the same acoustic pressure here, but it's a much easier problem to solve. And the solution is right here. This is the exact solution. You'll notice I put a minus sign here because that's the 180-degree phase difference. It could be up there, but we just might as well just take it. It can come down. You can put it right there. And you can see that when R plus equals R minus, that you get 0 at all times. So we make the approximation. I like this problem because you're going to be going through what we went through in lecture. And it's very important. This far field approximation is really important in acoustics and electromagnetic waves. So it's good to go through the calculation here, but in a different case. So before we had a plus sign here, remember? Now we have a minus sign. So instead of getting, e to the I something plus e to the I something is twice the cosine of that. With the minus sign, it's 2I times the sine, right? You all know that. So we have a sine instead of a cosine. The pressure amplitude, which is what we're usually interested in, we forget the I. That's just a phase factor. It's not important. Get rid of this and that. And we get this amplitude. So this is what we had before in lecture, except this is a sine now. We got a cosine before. And finally, the way that often acousticians characterize a radiation field is they go to the pressure nulls. So that's a common way to get a feeling for what it looks like. If we set the pressure amplitude equal to 0, and we don't want to miss any here, we want to get all of them, right? That means, what does this have to be if I'm going to get 0? Well, it's got to be n times pi, right? And n can start from 0. And this will be a subject, we're going to do these problems in the future, but I just want to point something out to you here. You can march off here with solutions, but eventually you're going to find there's an n max. All right, and it depends upon your wavelength. It depends on the KD value, this dimensionless quantity here. And you can see why that happens. If we solve for the sine of theta here, we get this, okay? Now eventually, for n is equal to 0, you get theta is equal to 0. One of the nodes is here, right? And incidentally, this is actually a cone. We have an axis of symmetry here. So we have these nodal cones that look like that. This is a cone with an angle of 90 degrees. We know this surface has to have 0 pressure amplitude. If it didn't come out here, we would have made a mistake, right? Because we're told that this is pressure release. So the n equals 0 corresponds to there. As you march up here in n values, you're going to get cones, okay? The next one will be here somewhere, then there'll be one up here. But what's going to eventually happen? Do you see what's the math telling you here? Eventually, this is going to be greater than 1. You won't have a solution. So there's only a finite number of cones, which I think is physically obvious. And how many you get depends upon the wavelength. The smaller the wavelength, the more cones you're going to get. Okay? So there will be some n max here. Okay. So we're going to do more of this. It's going to come up. It'll come up in the next chapter. This business of finding the nodal surfaces, in this case, nodal cones. Yeah. So we're going to do more of this. For that piston source, for example, we'll be doing that. Okay, any questions about this one? That's a good problem. This is the last problem, and this is interesting and relevant for underwater, for ocean, acoustics in the ocean. This is a shore. This causes the Navy a lot of problems. Sound waves near shore. Some of you probably are aware of that. So, I don't know about the research. I just know that from what I hear, that it's complicated problems when you have sound near the shore, and you can see why it's going to bounce off everything here, right? So it can be really difficult to find somebody or whatever you're trying to do. So here's the idea in this problem. This is 8.8. And you have to kind of stare at this a little while to see it. We're going to assume that here's the shore. We're modeling the shore as a straight thing here. And we're going to assume that there's a high specific acoustic impedance. We're going to assume it's rigid, just as an approximation. Okay? Here we have a pressure release condition for the surface here, the water. And here's a source. It looks like it's almost halfway. It could be anywhere in here, okay, the source. So we're going to look at two different situations here. The first one is we're going to suppose that the sound, first of all, bounces off the top and then the bottom. Okay, so I have a detector, let's say somewhere here. And we're going to first, in order to appreciate what's going on here, we're first going to consider sound waves that bounce off here first and then off there. How would I... all right, now, of course, it doesn't have to do that. It can bounce off here and then bounce off there. What else can it do? It can, there's a lot of possibilities here, right? And that's what makes this very complicated. So we're just going to focus on two possibilities here. The sound coming to the receiver will pick up sound from all kinds of reflections and all kinds of orders, different orders, okay? But one of them is going to be bouncing off here, bouncing off there, and then going there. I can calculate what that pressure is going to look like. And that's just part of the whole pressure, right? But we can calculate. How do we calculate it? Well, if it bounces off here first, I know how to handle, I know what that pressure wave, I know how to write it down exactly. I forget the surface, and I put an image source. Well, I forget the surface, except we want to put an image source equidistant on the other side. And because it's pressure release, I want this source to be, it'll have the same frequency, same amplitude, but it'll be 180 degrees out of phase. That was the problem we just did. Okay, so that's why I draw a circle here. So that gives me the wave that bounces off there. Now, so that wave is identical to the wave as it's coming from this image source. That's the beauty of the method of images. I can forget the surface here. The reflected wave from the surface is identical to the wave from there, the nice spherical wave, without the surface. That's the idea of the method of images. So I've got, this is now my source. Now it's going to bounce off here. So where's the image source for this image source? Okay, we're thinking this is a real source now. Where is its image source? Well, I have to go equidistant on the other side. And now do I put it in phase or out of phase? Well, it's a hard boundary, so it's going to be in phase. So I'm going to draw a circle there. So both of these are 180 degrees out of phase from the actual source. And now, if I have a receiver here, what it's going to pick up for this and only this situation, bouncing once off there and once off there, in that order, it's going to be whatever the nice spherical wave from there is. The problem, of course, is that you've got to add all these waves together, and how do you know, to figure it out and figure out where the source is can be a mess, right? Okay, so now you'll notice something here. Gee, and I didn't notice this, but you're asked to prove it in the book. Look at this point right here. These 2 points clearly lie on a circle, on the same circle with that as the center, right? Because we have this, because they're symmetric on either side of this radial arm coming here. So they're going to lie on a circle, right? Similarly, these two have to lie on a circle for the same reason. And because they share a point, right? Because this pair and this pair share that point, there's just going to be one circle here. All of these points lie on the same circle. And I wouldn't be surprised if people who have to deal with this, who write computer codes to try to unravel the sound here and do an inverse problem, right, to figure out where something is, they probably, this may be known. Anybody know? Maybe some of our distance learning students do. But anyway, I think this could be useful. I don't know how they do it. All I know it's a mess. That's all I know. Now, the other possibility we're going to look at is that we switch the order. Now it bounces off here first and then there. That's a different situation. The sound wave's going to be different, reaching the source here. So now we do, the first image source that we establish is this one. It's going to be solid. It's in phase, so I've drawn it solid. And now, for the reflection off the pressure release surface, I'm going to have a image source equidistant. I dropped the perpendicular here, and it's out 180 degrees out of phase. So now, if you've got a receiver here, what you're going to see for one reflection there and then one reflection there is identical to what's coming from there. It's just going to be a nice spherical wave coming from there. That's what you'll see in the region of interest. And again, because the source, all these points are going to lie in the same circle up here, right? Because the source lies on this. The source lies on a circle. I guess that's the best way to think of this. because the source is fixed, right? The images we're playing around with. So there's a circle with this is the center that passes through this source. And all of these points we've established lie on that circle. And you can see that these points also lie on the same circle. All of the points lie on the same circle. So, and people have probably utilized that. I don't know. Okay, so demonstrations this afternoon, about 15, 20 minutes, 2 groups. It's going to be videotaped. Gene has to leave town, but we got some people from an organization here to do it, and they'll edit it and then we'll post it. It'll be a while, right, Gene? Next week?
Yeah, Monday.
Oh, they'll be done with the editing?
Oh, I'm not sure I'll talk to Taylor.
We'll see. Yeah.
If Taylor just gives me the footage, I'll have it up.
Okay. Yeah, there's this group called the Center for Educational.
There's 3 Ds in there.
The Center for Education Design, Development, and Distribution.
Something like that. Yeah.
Or something like that. It's an actual organization here, and they're doing this, and we don't have to pay them. They get paid somewhere else. It's in their purview, or it's in their. This is part of what they do. Pardon me? Yeah, it's part of their job description. Right. Thank you.